Alright everyone, thanks for tuning in today to our random variables video lecture. In this lecture we're going to be covering the definition of random variables and how we apply them to actuarial problems. We're also going to look at various distributions, both continuous and discrete, that typically appear on actuarial exams. We're going to look at two continuous distributions, and we're going to look at one discrete distribution. We're also going to have one problem for each type, continuous and discrete. So let's just jump right into it. What is a random variable? A random variable is simply a function that maps from its domain to its range the real numbers or a subset of the real numbers. So that's the definition of what random variables are. They're a function, not necessarily how you might traditionally think of variables. So we're going to look at our continuous cases first, and then we're going to look at the one discrete case. So our first continuous distribution that we're going to be looking at is the uniform distribution. Our uniform distribution has the PDF, probability density function, 1 over b minus a. We also have the domain, inclusively x between a and b. For our uniform distribution, we have an expected value, or first moment, of a plus b over 2. We also have a variance of b minus a squared over 12. And we have an MGF, e to the tb minus e to the ta all over t times b minus a. So these are the key facts to remember about our uniform distribution. It's typically one that appears semi-frequently on actuarial exams, specifically the P exam. Next, we're going to look at the exponential distribution, which is probably the most common continuous distribution that appears on actuarial exams. At least for the P exam, it tends to appear quite a bit. So we're going to look at exponential. We're also going to be able to derive the moment generating function for exponential distributions, since we have a little bit more time in this video. So our PDF is lambda e to the negative lambda x, with the domain x is between 0 and infinity. We have a first moment of 1 over lambda. We have a variance of 1 over lambda squared. And we have an MGF that we're going to be able to derive. So we're going to review our definition of MGFs here. The expected value of e to the tx. We integrate across our domain. Now notice that we're integrating with respect to x, and I'm going to pull this over here. We have lambda from 0 to infinity, e to the negative lambda minus t times x dx. And if we actually go about integrating that, you'll get lambda minus lambda, just like this. So this is our MGF, our expected value, variance, and PDF. Those are all things that probably should be memorized just to improve your speed and your efficiency on the exam. So we're going to look at an example that came from the actuarial exam. This deals with exponential random variables, and it's problem 26.15. It reads, the time to failure of a component in an electronic device has exponential distribution with median of 4 hours. So our median is 4. Calculate the probability that the component will work without failing for at least 5 hours. So this is what we want, and we were given that our median is 4. So that means that this has to be true. The general form of our CDF for exponential distributions is 1 minus e to the negative x over theta for x greater than 0. Since our median is 4 hours, this has to be true. Therefore, this must be true. So all we did was substitute 4 in for here for this x, and we set that equal to 1/2, just like the problem said. Therefore, if we rearrange this and solve for theta, we'll obtain theta equals 4 over ln of 2. So, how do we get this? The probability that it will last at least 5 hours is equal to 1 minus the probability that it's less than 5 hours. So, all we have to do is do 1 minus our CDF at 5. So this is 1 minus e to the negative 5/4 natural log 2. So if we evaluate this and punch it in your calculator, you're going to get a probability of 0.42. So the crucial thing that we had to know was this right here. And we also had to know our CDF for exponential distributions, although if we knew our PDF, we could certainly derive that if we wanted to. So now we're going to shift our attention to discrete distributions, and we're only going to look at one today. The Poisson distribution is probably the single most important discrete distribution among those that appear on the P exam. We have a PMF of e to the negative lambda times lambda to the x over x factorial. Here x is 0, 1, 2, and so on. Our first moment is equal to lambda, as is our variance. If we were to derive our MGF, which we don't have time for right now, we would get e to the lambda times the quantity e to the t minus 1. So now all we have to do is apply these facts to our next problem, which is going to be 19.9. Problem 19.9 reads, an actuary has discovered that policyholders are 3 times as likely to file 2 claims as they are to file 4 claims. If the number of claims filed has a Poisson distribution, what is the variance of the number of claims filed? So we want the variance. We were told that they're 3 times as likely to file 2 claims as they are to file 4 claims. So, this is what we're being told essentially. We can now apply our PMF to this problem and figure out exactly what our variance is. So we have e to the negative lambda times lambda squared over 2 equals e to the negative lambda times lambda to the 4th over 4 factorial. 4 factorial is 24. We can simplify that. Notice that these will cancel if we divide by e to the negative lambda. So we can simplify there. And the same thing over here. If we were to divide by lambda squared, this would simplify to 1. And this would be lambda squared. So what we have is essentially 1/2 equals lambda squared over 8. So if we multiply by 8, we have 4 equals lambda squared. And remember, we wanted our variance for our random variable x. That's equal to lambda for our Poisson distribution. We have lambda squared equals 4. Therefore, lambda equals 2. So our variance equals 2. So not a hard problem, but definitely one that requires a little bit of knowledge into the Poisson distribution. This tends to be a favorite of professors and other faculty that teach actuarial courses. For some reason, they just seem to love this problem. It's definitely a good test for your knowledge of the Poisson PMF and just basic algebraic manipulation. But I don't believe the MGF has ever appeared on the P exam for Poisson distributions. Although I could be mistaken, it wasn't when I took it, but things change. So you can always refer back to this video, guys, if you ever just need to create a list of important facts for those 3 distributions. Unfortunately, we don't have time to do binomial, negative binomial, geometric, things like that. But we might be able to do another video on that sometime if someone else wants to pick up the project. So thanks for tuning in, guys. Have a nice day, and we'll see you next time.